Section 2.4, Angle Properties and Polygons. A polygon is a closed figure formed by joining three or more line segments at their endpoints. Polygons are classified according to the number of sides they have. So we know triangles have 3 sides, quadrilaterals have 4 sides, pentagons have 5 sides, hexagons 6 sides, and those are some of the ones. Octagons, most people know, is 8-sided. So it says in this section, we want to see if we can determine some of the measures of the inside angles of other polygons besides the triangle. So Giuseppe says that he can determine the sum of the measures of the interior angles of the quadrilateral shown by drawing a diagonal. So if you draw a diagonal from one vertex to a non-consecutive vertex, you get 2 triangles. And this would help us because if we kind of investigate this a little bit, we've got basically a bunch of different angles created here now. And basically, we know that the angles in this figure are angle 1, angle 2, and angle 5 together form another angle in the figure. Angle 3 and angle 4 together form another angle in the figure, and angle 6. So if we put that down, that the sum of angle 1 plus angle 2 and angle 3, and then we've got the other 3 angles, angle 4, angle 5, and angle 6. Basically, if you put all those angles together and added them up, you would get the 4 angles of the quadrilateral. And we know that these 3 together are 180 degrees because they're angles in a triangle, and these 3 together are 180 degrees because they're angles in a triangle, so that adds up to 360. So that gives us a method then to figure out some of the angles of larger polygons, because we can figure out how many triangles can be drawn if you connect the diagonals from one vertex to the non-consecutive vertices in the polygon. So the triangle we know is 180. We look at the chart below here now. And the quadrilateral, we know that we had, 2 triangles formed there, and 2 180s added up to 360. If we do a pentagon, I'll just do a quick sketch of a pentagon here. And we take from this vertex to here, and this vertex to here, we've got 3 triangles created, and 3 180s would be 540. And then this hexagon has 6 sides, which, it's not a real great one, but then if you connect from that vertex to all the non-consecutive vertices, you end up with 4 triangles, and 4 180s would be 720. And then similarly, if you did a 7-sided figure, you would end up with 5 triangles, and then 5 180s would be 900, I think. And the last one, if you had a 8-sided figure, an octagon, you would have 6 triangles that could be formed, so 6 180s adds up to be 1,080. And that leads us to the next, which we can generalize this into a formula, that if we can take the sum of the interior angles would equal n minus 2 times 180, because basically if you look back at those examples that we did, we had the number of sides take off 2 would give you the number of triangles that you would get created in that polygon, and then you can multiply that by 180. So if we use our formula to predict the sum of the measures of the interior angles of a dodecagon, we would know that the sum would be 12 take away 2 times 180, which is 10 times 180, which is 1,800. And there's some examples now below here to practice. So the first one says the sum of the interior angles of a dodecagon, so that would be the sum would be n minus 2 times 180 would be our formula. And that would equal, in this case, 10 take away 2, or 8 times 180, which is 1440, yeah. 1,440 degrees would be the sum of all the interior angles of a 10-sided polygon. Determine the measure of each interior angle of a regular hexagon. For the first thing we need to know is what the sum of the interior angles would be. So that would be 6 take away 2 times 180, which is 4 times 180, or 720. And therefore, a regular hexagon has, when you see the word regular in front of a polygon, that means all angles are equal in measure and all sides equal. So if they're all equal, each angle should be 720 divided by, there were 6 sides, so that means there's going to be 6 angles, so that would give you 120. Each angle should be 120. And the next page here now has some more problems. So the first one here, you got to determine the missing measure. Well, this is a 4-sided figure, which implies is going to be 360-degree sum for the angles. Because a quadrilateral should know that one, shouldn't have to use formula for that one. So therefore, x should equal 360, take off the 94, take off the 86, take off the 135-degree angles. And because you know they all have to add up to 360, so if you just basically take those away from 360, you'll see what's left for the angle x. 45 degrees. And similarly for number 4, now that's count the number of sides there. 1, 2, 3, 4, 5, 6 sides. So 6-sided figure, we just did it a few minutes ago, but if you can't remember, the sum should be 6 take away 2 times 180, which would be 4 times 180, or 720. And therefore, x should be 720 then. Take off all those angles. Take off the 138, and the 115, and the 131, and the 127, and the 150-degree angle. So 720, take off 138 minus 105 minus 31 minus 27, and the 150 leaves you with 59 degrees for x. And the last question, how many sides does a polygon have if the sum of its interior angles is 1440? Well, if your sum is n minus 2 times 180, we go back to our formula, and we know that this is 1440. We know the answer to that, and we don't know what the n is. What we can do now to isolate the term with n in it, we can basically divide the 180 out of both sides. So that's going to give us 1440 divided by 180 is 8. So we end up with 8 equals n minus 2. So if we solve for n now, we get 8 plus 2 is n. So n would be 10 sides. All right, so there's some extra questions on page 99 to 101 there now that you can try.